recording and I will start giving a talk. So welcome everybody. So today I was promising to give you some results on moduli spaces and gluing theorems, but first we need to finish the proof of Poincare conjecture in dimensions 6 and more, because we just gathered most of the tools that are needed, but we didn't dotted T's and dotted I's and crossed T's. So let me just start. So theorem: if M is simply connected, dim M is greater than 5, and H star of M is equal of H star to S of the corresponding dimension, then M is homeomorphic to S of this dimension. Okay, so there is a variant of this theorem. If W is an n-dimensional manifold with boundary V0, V1, V0, V1, n is greater than 5, H star of W V0 is equal to H star of W V1, and pi 1 of W is 0, then W is homeomorphic to, actually here it's diffeomorphic to V0 cross 0, 1. So this condition is called the condition H cobordism. Let's call it H cobordism. H, that it is being a manifold that bounds a disjoint sum of two manifolds means that W is a cobordism between V0 and V1. And this condition means it's a H cobordism. So this is an extra condition, and then this is the product. So these two theorems are tightly related. We will prove this one. If you go to Milnor's book, Milnor gives the proof of the slightly more general one. But the techniques are the same, except for you have a closed manifold in here, and here you have a manifold with boundary. So you use, for this you use a Morse Witten chain complex, and for this you use analogous construction, which we didn't do, so that's why we focus more on that. And while I'm saying about Morse Witten chain complex, this chain complex is the theorem that homology of the chain complex is equal to the singular homology is actually proved in Milnor's book. So I read Milnor's book several times, but I didn't pay attention to that fact. But there is a proof of the theorem in Milnor's H cobordism book. Probably this theorem was well known to Smale. So Smale is the author of this theorem. So okay, so let me just start proving this theorem. So this is the subject for at least part of the talk of today. So proof. Well, our proof is try to simplify a Morse function. So take a Morse function on take a Morse function on M, so f m to r, any Morse function, and then try to simplify it over and over to make sure that it has precisely one minimum and one maximum. And so we invoke the result that was proved during the classes. So we want to simplify. First step, choose f to be self-indexing. That is, critical points of f are all of index k are at level set k. So level set k or level set f inverse of k. So this is like first step, and this is, well, this is what we already done. So this is like checked. Second step. Make sure that there is precisely one local minimum and one local maximum. And this is already what we did during classes. We did it once, so the second step is already checked. And the third step is, well, we write, before I start tell you what is the first step, I will tell you what is the fourth step, and I will explain to you why the third step is needed. So in the fourth step, we write down the chain complex, Morse mail width and chain complex, and then we try to show that it is, well, acyclic except in dimension in degrees 0 and n. So we can find pairs of critical points that are, by the basis theorem, we can find pairs of critical points. And Marcin, I will explain, recall what the basis theorem is later on. And then we can cancel them by using Whitney trick and simplify the function. So this will be the fourth step. But then the Whitney trick had this requirement that doesn't allow you to cancel pairs of 1, 2 critical points. So if you have a critical point of index 1 and critical point of index 2, and they are connected by several trajectories, but that the signed count of these trajectories is equal to plus or minus 1, then you cannot play the Whitney trick because the dimension is too small. So that was the assumption that something couldn't have too large dimension. Let me just show you on the lecture notes from the last classes. Where is this assumption? Well, actually, it was only for b less than f inverse of c minus 2, but okay. So this was the assumption that we couldn't use the Whitney trick to cancel critical points of index 1 and 2. And getting rid of critical points of index 1 is important because we want the level set to be simply connected. So you look at level sets, the Whitney trick is played on the level sets, and you want level sets to be simply connected. But if you pass above critical points of index 1, the level sets are not simply connected because you just, index 1 critical points just create loops. All right, so that's what we already did during classes as well. So we need to get rid of critical points of index 2. Third step. This should be first step. And this is the step that we didn't discuss it before. I just announced it. Get rid of critical points of index 1. And here is a trick. So this step will take like next 20 minutes of our talk, or maybe even more. So about third step. The idea is completely different than for the zero index critical points. You would like to say, well, okay, we have an index 1 critical point, we have index 2, we have a pair, we just do something with that pair. No, it doesn't work. Or at least Milnor didn't work it out. That's which basically means the same. So idea, trade critical points of index 1 for critical points of index 3. So, okay, so that's idea. More precisely, introduce. So first we spoil the function, and then we will first we spoil the function, and then we repair it. So it's like twice what usual governments do. They do the first step and then they stop, but we will continue. So more precisely, first introduce a pair of critical points of index 2 and 3 in such a way that we can cancel the resulting pair of 1, 2 critical points. So in the picture like we could have, and Dorota, this picture will sound familiar to you. We have trajectories from index 1, 2, 3, and if you have a situation like this, we can either cancel this pair of critical points or this pair of critical points. So we will create for a critical point of index 1, we will create a pair of index 2 and 3 critical points, and then we will cancel the 1, 2 critical points, so we are left over with the index 3 critical point. So that's what we will do. And I don't know why this picture reminds me of plumbing calculus for surface singularities, but it's probably not that related, but the idea is similar. Okay, so more precisely, so how do we start? First, we need, of course, we need to be careful. So if we need to introduce the critical point of index 2, we need to make sure that it forms a canceling pair with the critical point of index 1. So let me call it m1/2. Here we have f inverse of 3/2, f inverse of 5/2. Okay, and we have critical points, so we have level sets, and maybe these critical points should be drawn like this, and maybe like that. And of course, below the level set f inverse of half, below that, we have just precisely one critical point. So this is as n-1, n is dimension of m. If you work with this H cobordism theorem, then this is not Sn minus one, but it's a simple connected and simply connected manifold. So it's almost like Sn minus one for our perspective. Okay. So what we start with an index one critical point over here. So we have the unstable manifold, which is these guys form Sn minus 2. Sn minus 2 is the codimension 1 subspace in the level set. Okay, this guy has dimension m3 over half. So dim m3 over half is n minus 1. And the codimension of this sphere m3 over half m3 over half is equal to 1. So on the picture, the situation looks like, I will keep the picture over here. So we have m3 over half, and we have the sphere. So this is codimension 1. So I choose any point on the sphere, and I choose an arc and this arc is it's just a piece of an arc crossing Sn minus 1 transversely. So this is like a beginning of our stable manifold, essentially beginning of the stable manifold of the index 2 critical point we are about to introduce. And this arc, well, index 2 critical points have the stable manifold that is the sphere that intersects with the level set as a sphere, as a circle S1. So we need to complete this arc in such a way that it doesn't intersect any of stable manifolds of the critical point. So what we do, we have like 2 points over here, which are endpoints. So maybe these points should be magenta, which are endpoints. We flow it. So if we say, well, we have a Morse mail vector field, so we flow it by the vector field back to this level set. Okay, and once we have flown it, well, these endpoints are not on the stable manifold, on the unstable manifold of any critical point of index 1, because they are just away. So the flow of psi, psi is the vector field, psi gradient like. So the flow of psi takes these 2 points back to the level set m half. Well, that's that's what we do. And now these 2 points, this space is connected because we have only one critical. We have precisely one critical point of index 0. So this one handle, none of one handle makes 2 disconnected things connected, because that's what we got in read in the second step. All right, so these points are in the same connected component of m half because there is only one connected component. So on m half, we can always connect them by an arc gamma. And now we connect them, but we want to connect them in such a way that they don't intersect any of the stable manifolds of this, because we want to then to flow gamma back to this level set. All right, so what is what is the reason that it doesn't intersect? So it's the first place where we use the dimension assumption. So maybe we resume recording. So we have what is happening on M1 half. So we have these two endpoints, the purple endpoints, these purple endpoints. We have an arc gamma, but we have also the stable manifolds of index 1 critical points. But index 1 critical points intersect level sets, stable manifolds of index at pairs of points. That's what is index 1 critical point. Index 1 critical point has stable manifold of dimension 1, and it just intersects level set along S0. So since dimension of M1 half is greater than 1, so this is where we use that n is greater or equal than 2, we can choose gamma so as to avoid stable manifolds of index 1 critical points. But then we come back to that picture, we have gamma, we flow this gamma back to here. So we have a loop which we call gamma, capital gamma, which is a circle over here that intersects our Sn-1 in precisely 1 point. Okay, so this is not the end of the story. So let me just, this picture will be important in the...
Why does the, can you please repeat why we have the circle that intersects Sn-1 in precisely 1 point?
Oh, because we start with this red arc, yes? We take the endpoints, and this red arc intersects this Sn-1 in precisely 1 point.
Ah.
Okay?
Okay.
And then we cap it by the part from here that closes the arc from the other side.
Mm-hmm. Okay, thanks.
Okay. So
thanks.
Copied it, but it didn't work. Okay, maybe I should do it once again. Okay, so here we are. And now I have the cycle gamma in here. And I can put gamma as dimension, as n is greater than 3, we can make, by the same argument as above, we can make gamma disjoint from from stable manifolds of index 2 critical points. Okay, so we can flow gamma to the level set M half. So I call it gamma again. And why do I flow it to this level set? Well, the reason I want to work over this level set is that this level set is simply connected. So claim m5 over half is simply connected. And I think I will leave it as a homework. Probably it's it's basically what we did or almost did. If it's not simply connected, then higher critical points will not kill any loop that has appeared. So from the simple if the whole of M is simply connected, then after we pass through 1 and 2 handles, everything is simply connected. All right, so this is something that I leave as an exercise.
I have a question because let's say to propagate the endpoints, we used our Morse mail vector field, and
Yeah.
it's right.
Yeah.
And where did we do we have some arbitrary Morse function on the manifold, right?
Yeah.
And the question is, where did we get the vector field from? Is it just arbitrary?
Arbitrary gradient like vector field for the function.
Okay, thanks.
Okay. So m5 over 2 is simply connected. And then the next part of the third step of the proof is that I want to create on a nearby level set, I want to create a canceling pair of critical points. So I want to spoil the function f. So next half step or semi-step is spoiling the function, i.e. introducing a pair of critical points. So this is a fairly general procedure. Like you have a function, you can introduce a pair of critical points basically out of nowhere. And Milnor gives a recipe for that. But actually for this part, I prefer as a reference the paper of Cerf in IHES. It's, I think, 1970. The subsection on the key part, the paper is in French, chemin élémentaire de naissance. That elementary path of birth. Cerf also uses elementary path of death, and I like the connection of the sound of it with Indiana Jones movies. But this is a slightly better and slightly more precise approach. The key point is that I don't give you a pinpoint reference for that paper, because the references to that paper are, well, the numeration of sections and subsections is a bit dubious in that paper. So it's basically better to look to find the PDF file and check up the part the way you read it. So it's not intuitive to give, if I give you chapter 5, section 3.52, much harder to find. Okay, so what do? We start with an auxiliary function, which I call B, like birth, of x1, xn. Let me just copy it from my minus x, or I will call it b tau with subscript tau, k square plus xk plus 1 square plus xn minus 1 squared, and now xn cube minus 2 tau minus 1. Let's put epsilon xn, where epsilon is a parameter, and tau is in 0, 1. Okay, I used it in my previous recent paper, and um, mm, mm, and so and I just found a mistake in that paper, so and not one in this part, so that's a pity. It's not very good to copy paper parts from the paper you write, because you find mistakes. Okay, so this is what is happening with that function. So this function depends on a parameter tau, and for tau equal to 0, the function has no critical points. So this is like this part is like for making it multidimensional. This part is something that you need to understand. So how do you understand it? Well, let me draw a graph of the function. If tau is 0, then this is like xn3, xn cube minus plus x1. So this is a function that plus xn. So this is the function that looks like, I'm not very good at drawing cubic functions, but let me draw it. For tau equal 1/2, we have this. Tau less than 1/2, it's like this. Tau greater than 1/2. Okay, so this tells you that this point or that point are critical points of this one variable function, and then if you combine it with this part, you get function that is that is sorry, you get a function that is that has precisely two critical points, that is an variable function. So you start with something that has no variables, so then you have a non-Morse critical point over here, and then you have two critical points. And of course, you can view it as from different perspectives. So if you are an expert in dynamical systems, you view it as a saddle node bifurcation, which I already explained to you. Or if you are a singularity theory expert, you view it as a bifurcation diagram of a D4, sorry, of an A2 singularity, so in here. But the key point is, no matter how you look at it, you introduce pair of critical points. Okay, so let me just, and this epsilon is a parameter that I will discuss in a moment. So let me just improve on this function slightly, because this function, well, depends on the parameter tau, not only locally, but also globally. And I would like to have a function that is somehow injected into my Morse function, so that I want to, and for that purpose, I want to control it, to have it fixed on the boundary. So fixed, sorry, not on the boundary, fixed away from a small circle, small ball in Rn. So what is the function? Well, introduce a bump function omega from Rn to R, supported on U, where U is some ball in Rn. So we do it locally. So first we are abstracting from the function. The function will appear later on. So some ball in Rn. equal to 1. Sorry, so maybe let me be more precise. 0, 1 equal to 1 in a neighborhood of 0. Okay, so this is like a standard function, and then we define b tau omega of x1 xn equal minus 1 x squared minus h a square xk square plus hk plus 1 square plus hn square hn minus 1 square plus h minus, and now 2 tau minus 1 epsilon omega xn. So here I introduce the parameter. Sorry, 2 tau, it's wrong, it should be 2 tau omega minus 1 epsilon xn. So what is happening, if I introduce here this parameter omega, then my function will be equal to b tau omega is equal to p tau close to 0, and b tau omega is equal to p0 away from you. Okay, that is what we are doing here. And now remark, b tau omega has the same crits as b tau if epsilon is sufficiently small. Okay, so we do slightly the opposite. So I first introduced epsilon, and now I introduce omega, but then I adjust epsilon to omega. And this is like something that you would like to check, or probably don't want to check, that, what can go wrong here is that, well, if omega is equal to 1, then of course the critical points are the same. If omega is equal to 0, then there are no critical points. So the key part is in this, the key part of this homework, or something that you have on you, and you have a subset omega is equal to 1, the key problem is in this yellow region. So this is a place where you have to be careful and show that there are no critical, that if epsilon is sufficiently small, there are no critical points of this p tau omega function in this region. How you do it? Well, you first look at the derivatives of omega, and these derivatives of omega are finite. Okay, so they may be large because your set u can be very, very small, so omega, but you don't care. They are bounded. They are bounded on the whole of Rn. And then you see, well, if you are away from this set, then the derivatives of this guy, so derivatives of b tau, are bounded away from 0. And you can get some bound. So then if you define, like, for example, the length of the, the derivatives are bounded, for example, the length of the gradient, which is quite a good bound for it. And then you see, okay, if I take epsilon sufficiently small, then the length of the gradient of epsilon omega will be very, very small in this region, will be very, very small when compared to the length of the gradient of b tau. And then I can say, well, okay, if my original function didn't have critical points, then this length of the gradient of the 2-by triangle inequality can be is positive. So that gives you the fact that there are no critical points in that region. And of course, you can do your calculations in the way you prefer the most. So the point is that we have like the formation of a function, of a B0 function, or a path starting from the B0 function that is supported in the set U. So away of U, the path is constant. And this path introduces a critical point on a critical point on omega. Sorry, on Rn. So a pair of critical points, and this k is a parameter, and you probably have guessed that this path introduces a pair of critical points, one of index k, one of index k plus 1. So just for our purpose, you just set k equal to 2. Okay, so now the last part is to inject b tau omega.
Can you repeat why we get 2 new critical points from such a device?
Well, for that, is it clear for you that this function acquires two critical points?
Yes.
Okay, so then when you perturb it, you just want to make sure that these critical points sit in here.
Okay, yeah, and perturbing doesn't change critical points. Okay, right. Thanks.
Maybe you need to restrict to a path, the path, so that these two critical points do not go out of this region where omega is 1. So instead of going back up to with tau up to 1, you go up to tau equal 1/2 plus something, but it really doesn't matter. This is like a very technical detail. So what I do is I want to use first implicit function theorem. So I first define a diffeomorphism psi from Rn to Rn, which is given psi of x1 xn is equal to x1 xn minus 1 b0 of x1 xn. So now, what is b0 composed with psi inverse? So this is a diffeomorphism. You can check that this by theorem of local diffeomorphism, because b0 by the definition has not vanishing derivative with respect to xn. Okay, so x derivative of xn of b0 is just this. So b0 with respect to xn behaves like this, like xn cubed plus xn. So the derivative is non-zero. So this is a local diffeomorphism. Actually, it's a global diffeomorphism if you look at it carefully. So what is b0 composed with psi inverse? Well, any guesses? What is this function? Okay, if you didn't guess, let me give you it's equal to xn. All right, so this is like if you pass from this to via inverse of psi and then you compose with the b0, then you're just then you just the composition just singles out the last variable of this function. Okay, so now we define a path which I will call b tilde tau omega to be b tau omega composed with psi inverse, and then b is xn. Okay, and this path introduces, and b takes a neighborhood. Sorry, is equal to b is equal to xn away from an open subset, open and bounded subset V of Rn. Why the subset V is bounded? Any ideas? Why we can introduce, so B0 was defined to be equal to, so beta omega, this guy, was defined to be equal to B0 away from an open subset from an open ball U in Rn. So why is it true that B0 omega is away from some ball V in Rn, bounded? Is it obvious if we take any psi, any possible psi that it will be true?
Well, one guess, but it's just a guess. Would be that it might have something to do with the fact that the bump functions have compact support.
Not yet, because bump function, well, yes, bump function have compact support means that U is bounded, but there is something more in it. Something that we need to check, and I didn't check, and but I don't want to put it under the rider. There are too many things under the ride by now. Okay, so let me just give you an answer. Psi is a proper map. It bounds bounded sets to bounded sets. So B0 is a proper function. So this map is proper. And properness means that you map, and its inverse is proper, that you map compact sets to compact sets. If it's not proper, then the preimage can be, the preimage of the inverse can be unbounded. Or psi actually is, since we do it psi, we mean just psi is a bounded function. So you need to just say one sentence that psi inverse takes compact sets to compact sets. Okay.
I'm confused with one thing is because you first we write that B0 to B tilde equals to xn, and then we repeat it, but with the claim that only away from a subset. So
because there is a typo. It's beta of omega for all tau.
And how are we actually? Why noticing that psi is proper? I mean, so that's the trick for in this case.
Well, because we have U psi V. Well, actually, it's simpler a bit. It's a bit simpler. So we know that b tau equal b tau omega equal B0 in the whole of the green part, and we know that b tilde tau omega is equal b tilde 0 equal xn minus 1 in the whole of this part. Okay.
Okay, thanks.
All right, so that's the point. So now we come back to our manifold M, look at a point on the level set. Choose any point z at the level set m, let's say 2 plus 3 over 4. Okay, so we are past, we have like m2 plus 1 half, we have here m3 plus 1 half, so we are, but we have like m2 plus 3 over 4. So before we have index 3 critical point, but after we had index 2 critical points. 2, these are index 3 critical points. And we choose a point z. And now there is a statement that there exists a neighborhood W in M, not in a level set, but in the whole of M of Z with local coordinates let's say y1 up to yn, such that f restricted to W is equal yn. Okay, is it clear? Or do you need? This is the same, essentially the same operation as in here. So what do you do? Anybody wants to hear the proof of that fact?
I have a question to the statement. F is our Morse function, or?
Yes, f is our Morse function, yes.
Okay.
The Morse function that is going to be spoiled. Okay. Sketch of proof. Choose any coordinate neighborhood of v tilde of z with coordinates y1 tilde, yn tilde, and then we have well, at least for one of the for at least one index I. Okay, for otherwise, if this is not the case, we know that z is a critical point of f. But since we know that z is not a critical point of f, at least one of the derivatives is non-zero. So without loss of generality, suppose df over dy n tilde of z is non-zero, shrinking f if shrinking w if needed, leads to, sorry, we can assume that df over dyn has fixed sign on w, and now we define psi yn to y1 yn minus 1 yn, and so sorry, or we just say, just define, or maybe I will be a bit quicker. Define y1 equal y1 tilde, yn minus 1 equal yn tilde, minus 1 tilde, yn equal f of y1 yn. So this is a base change. In these coordinates, the function f is equal yn. And this gives you a local diffeomorphism that changes one coordinate system to the other. So if you shrink w tilde to w, this is a local diffeomorphism on some w containing z. And this is the reason why this is the same argument as we have in here. Okay, this is the same argument involving implicit function theorem. So implicit function theorem is used for that purpose and not for checking if something given by a set of three equations and two inequalities happens to be a manifold, as you were probably more used to that kind of problems. This is like the standard usage of the implicit function theorem. Okay, so this proves the claim. And now what is this? I am on M, I have Z, I have W. So over here I have a map over local chart with coordinates y1, yn. So this is like some set U in Rn, and my function f is equal to y1, yn. Okay, so what do I do? Now it's adjust. Now we inject our function beta tilde, beta omega, we inject it in here. So adjust omega so that it's supported in U, in this U, this particular U. I use the same U as before on purpose. So adjusted and epsilon as above to construct a path f tau equal to f away from W and beta omega in W. And beta omega in W by identifying this part and that part. Okay, so there's one thing I want to control. So my function f 1/2 plus some delta has two grids. I still want to control the gradient like vector field. vector field for, let me call it this f tilde for f tilde. So what do? We just take slightly small, slightly larger or slightly smaller. That is basically your the matter of taste. Neighborhood W0, bump function phi from m to 0, 1 on W on equal to 1 on W0 away from W0, and psi tilde a gradient like vector field for f tilde on W0. So we take any gradient like vector field for our for our new function over here, and then we do the fantastic thing that which we can do about gradient like vector fields. We define psi tilde. Sorry, maybe I should call it this psi naught to be equal to phi psi naught plus 1 minus phi psi, so that away from this set, my new gradient like vector field is the same as my old gradient like vector field. Okay, so that I spoil my function of my gradient like vector field in the neighborhood of z, but I keep control over both the function and the gradient like vector field away from a small neighborhood of z. Okay, that I want to have because I insisted before, that I have this sphere, this circle that it intersects my ascending sphere of the x1 critical point precisely at one point. So if I spoil my vector field too much, if I take a random vector field, I have to start over. But I just take, okay, I have a something that is good in here, but I spoil my function over here. So let's see what is the situation. Maybe I need to copy the picture again, and I need to update the picture for the situation. And now I need to enlarge this picture. Oh, I won't enlarge it. Okay. So or maybe I can enlarge it. Okay. So what is the situation? I have here f inverse of 3/4 plus 2. I have my critical point z. And then, lo and behold, what is going on? I introduce a pair of critical points. So index 2 and index 3 critical points. And over here, I have a stable manifold of the index 2 critical point and some trajectories and so on. But the key point is that I have here a sphere S1 at the level set well f psi f inverse of 2 plus 2 over 3. And I have another sphere that is at this, or maybe I can also flow this sphere. So I have here my sphere gamma, and I have here my sphere maybe not that color. I have here another sphere that is the stable manifold. Let me call it gamma prime. Gamma prime is the stable manifold. But now I have like two spheres inside of this manifold, and they have no reason to be the same. There's no reason why gamma should be equal to gamma prime. Well, gamma is one sphere, gamma prime is another sphere. But then we have, like abstractly, we have two embeddings, S1 into F inverse of 5 over 2. And now the dimension of M5 over 2 is greater than 4. That's our assumption. And now any two embeddings of S1, this is like Whitney theorem, any two embeddings of S1 into a four-dimensional space are isotopic. So I can find a homotopy or an isotopy that takes one sphere to another. They are not equal, but they can be made but they are isotopic. So what I do, yeah. So there's no
Are we using some theorem from the previous lecture at this point?
Not yet. This is a theorem that two embeddings of S1 into four-dimensional space are isotopic. This is a variant of Whitney's embedding theorem.
This is this theorem that any abstract manifold can be embedded in Rn.
Well, no, there is a Whitney theorem is something. So, well, this what you said is a bit weaker than the general statement. So, general statement of Whitney is that any manifold, any map from a manifold of dimension n to a 2n-dimensional manifold can be perturbed to be an embedding, and if the dimension is larger, so the threshold dimension for one-dimensional spaces is 4, then any two embeddings are isotopic, true embeddings. And that's what we use here. Okay.
So I understand that this is something that we don't prove, that we just accept.
This is like Whitney theorem.
Okay, thanks.
We can prove it. Well, I can prove it using Morse theory, but it's like another 5 lectures probably. Maybe the next 5 lectures, but okay. So I have an isotopy that of this space that takes S1 to one of these spheres to another, and I inject this isotopy by isotopy injection theorem over here, so that these two critical points, these two circles match. So in this last stage, I essentially match the two circles by changing the vector field size. So Marcin, you asked at the beginning, what do we do? How do we choose our gradient-like vector field? First approximation is we choose it randomly, but then we improve on it in such a way that in here it injects precisely the isotopy that takes gamma to gamma prime. And so with this new vector field, well, it doesn't change anything before. This gamma over here is the stable manifold of this critical point, index 2 critical point that we have created. And then we pass it over here. And I forgot one thing to say. I said we use Whitney theorem, but Whitney theorem says that any two homotopic embeddings are isotopic, and they are homotopic because this space is simply connected. So we use the fact that this is simply connected space. If they are not simply connected, then there is an abstraction. They can represent two different homotopy classes. If we have two circles that represent two different homotopy classes, then no matter how you try, you won't find an isotopy between them. But anyway, we have created an index 2 critical point and index 3, and this index 2 critical point has precisely one trajectory from index 1 to index 2 critical point. So now we rearrange, so we are allowed to move this critical point over here and then cancel. We can now cancel the resulting pair of 2, 3 critical points. So there is one comment over in here. So it took me like not 20 minutes, but an hour. And we do it, of course, with every critical point of index 1. So here is an interesting statement that, well, we really assume we don't use Whitney trick yet, but we really assume that the dimension is 4. If dimension is 3, if the dimension of the whole manifold is 4, so then we can have like 2 handles that are non-trivially knotted in on the level set. So there is a way of dealing with this critical. So first of all, it is not known if any simply connected manifold admits a function, Morse function with. Wait, no. I think it's not known that it's not true that any simply connected manifold admits a Morse function with no critical point of index 1. There are some abstractions and some examples where you can prove that there has to be one critical point. I think it's in Marco Gola's paper. I won't check if he's on chat now. But there is a way of looking at index 2 and 1 critical points on 4 manifolds, which is called Kirby calculus, which is a very geometric way, and the reference for that is Gomp steep siege. I should write it maybe in. One is Gomp steep siege. And there is a recent book, which is probably available online, of Selman Agbulut, who is a grandmaster of Kirby calculus. But if you say it to him, he will be a bit angry because he thinks he's a more 4-dimensional geometrist. But in fact, this person is like mastered the Kirby calculus and count of handles on 1 and 2 handles to a level that is beyond human imagination. So he's like Leo Messi of 4-dimensional geometry in that aspect. So this is like the end of step 3. So where we are, let me recall. We have a function f from M to R, self-indexing without index 1 crits. So all level sets, all non-critical level sets are simply connected. So now we do the procedure. We pass to step 4, canceling critical points. And canceling is using the approach that I sketched during last lecture. So we have a chain complex Cn, Morse smale with a chain complex Cn minus 1 goes to C2, goes to C0, goes to 0, because there is no there is no there are no critical points of index 1. So this is a 0 map. And now we have C2 has a basis. Let's say C21, C2K. So this is the complex is acyclic. So homology, second homology is 0. Okay. Second homology is 0. So this complex is acyclic in this part. In particular, this map from C3. Let me just write C3 over here. From C3 to C2 is surjective. So there is a there are elements C31, C3K in C3 such that the boundary of C3 is 3I is C2I. Okay? And now I look at the subgroup spanned by C31, let's say capital, spanned by C3K is a direct summand of C3, and this is like an exercise, a simple remark in algebra that it's a direct summand, because if it's not, then you have the map. So we like can extend it to a. So if it's not a direct summand, then it's like a multiple of some direct summand. So some of the elements are multiple of generators. And then this map, since this is surjective, this surjects, then there will be some torsion in homology of C3. So if it's not a direct summand, then it's a homology of C3. In particular, C31 up to C3K can be completed to a basis of C3. Okay, so this is like an observation, and now we use basis theorem to obtain from lecture 9 to improve actually the vector field psi and maybe the function f, so that C31, C3 S and C21, C2K are actually represented by the critical points. So we have a basis, but this basis is like, this basis can be like, originally this basis can be some linear combination of C1 up to C21 to C2K or C31 to C2N. So this can be like a linear combination of one and linear combination of the other. But now we can say, well, we can perform Handel slides from last lecture to obtain that this basis, that each element of this basis is precisely a class of a singular point. So Marcin, that is one of the statements of the previous lecture, and I think this is like what I should do over here. So in
I have one question regarding the thing that was on the previous page. Can you please repeat why we know that the subgroup spanned by these elements that generate C2 is a direct sum? Because for modules we don't always have a direct complement. Basically,
well, this is a free group, free abelian group, and surjects with the and the kernel. So okay, so you have C3, okay. So in C3 you have the subgroup that is kernel of C3 and the image of C4. Sorry, kernel image of D4, kernel of D3. So I would say that the image of D4. So this is the kernel is a direct summand. Okay, the kernel of a map is a direct summand. If I'm not saying any very stupid thing, because I need to cook up the.
Let's consider Z4 and multiplication by 2. Then Z4 doesn't split. But if we knew that C2 is projective.
Wait. No, not that. This doesn't follow from projectivity. This follows from the fact that the kernel of D3 is a direct summand, and then the kernel of D3 is a direct summand, so we can write C3 is kernel of D3 plus some subspace C3 tilde.
And why is the kernel a direct summand? Here.
Okay, can we discuss it during classes, because
Yes.
it's can start with it, because it's I don't want to say something very stupid, and I want to compute to conclude the proof. So in particular, the C3I is equal to C2I. So there, the count of trajectories from C3I to C2I is +1. So the count of trajectories, which is like we can have like from this critical point C3I to C2I, we can have many trajectories, but they come with signs. Each trajectory comes with signs plus or minus, and the signed count, so those with sign plus and those with sign minus are in total those with sign plus are counted positive. With sign count minus are subtracted. So the difference is +1. That's a homological statement. And now by Whitney trick, we can alter psi in such a way that there is a single trajectory from C3I to C2I. So we can cancel this pair without affecting other critical points, and then we move on and on and on until we have cancelled. We repeat the procedure until we've cancelled all crits of index 2. And now we pass to critical points of index 3. and so on. All right, so once we have cancelled, we pass to index 3 critical points and so on and so on. And in the end of the day, we just say, okay, this is what we did. So this is the end of the proof of Smale theorem, and moduli spaces will come next year. So that's all for the lecture, and we will resume at 10:15 with classes and start with the classes with this algebraic question.
I have one question regarding to the finishing of this, the way we concluded, because now we don't have any index 1 critical points, but then we still have some kind of higher index critical points. And for the lemma from the classes to work, we need to have precisely one minimum, precisely one maximum.
Wait, we have like this is one dimensional, this is one dimensional, this we cancel. And then once we got rid of that, we work with this, and then we cancel this until we arrive at the situation when only these two remain. And then we can cancel this. And then eventually we end up with Cn, and Cn is just one generator. If you are afraid of why can we cancel these critical points, well, if you are in dimension more than how much 5 in dimension, if n is greater than 5, we can play the same game as in step 3 to trade index Cn minus 1 critical points for index Cn minus 3 critical points. So if n is greater than 5, then you can get rid of critical points of this index as well, if that helps you. But we already assume that n is greater than 5. Actually, so you can get rid of these critical points as well. Anyway, this is like the conclusion. Any other question?
We just claim that we are getting rid of the higher level, higher index critical points in a completely analogous way to the
to index 2 critical points. Yes.
Thank you.
This is like the version of induction that I start with C2 and say, well, next are done the same, but I could assume that we have cancelled all and we pass to induction step to be more formal, but I think it's okay. So I think it's the same. Are there other questions? If no, so we resume at 10:15.